So we're going to go over the test, and I'm going to go through each answer and how much it was worth, and what I look for in the grading. And this is a good opportunity for you to go through and see if I messed up and correct me and tell me I did it wrong and get a better grade, I guess. Okay, so number one. How is raster GIS data similar to an image that is stored digitally on a computer? How is it different? Okay, so I was looking in the similarities. I was looking for it's still an evenly spaced set of numbers. Okay, it's numbers on disk that are organized into rows and columns, something like that. And then how is it different? I was looking for that it's spatially referenced. Okay. And so each of those were worth 1 point. When converting from raster to vector format, is it possible to do so without loss in data or accuracy? No, it's not. Why? Because the spatial location will have to be approximated to the grid. So when you're going from vector to raster, the most precise location we can get is the center point of every grid cell, and so we're locked down to that grid. And what are the trade-offs? The trade-offs are that what I was looking for here was basically, well, you can make your cell size smaller, but you're going to increase your data size. That's the trade-off I was looking for, the answer. So that was worth 3 there. Okay, give an example of a scale model that is used in GIS practice. Okay. A scale model is basically something that's a small representation of something that's real. Now, in GIS, we deal with usually virtual scale models. We can't actually touch it, but any map, any data layer would be a good example of a scale model. Okay. But it's not abstract other than the fact that it's stored on a computer. It's still a scaled down version of reality. So I guess one of the things I'm trying to say is that if you put something that was really a mathematical model, was modeling a process, and then you would have gotten that one wrong. All right. And try to get partial credit. So sometimes you got something wrong there. Okay. Give an example of a mathematical model. Here there are lots of choices that we went over. Pretty much all of the things that we talked about in terms of slope and runoff and those things are mathematical models that are used to describe a real-life phenomenon using a mathematical function. And most of the examples we went over were deterministic, which means that the mathematical model only produces one answer every time, the same answer every time. Okay. We didn't really cover any stochastic models yet, but a stochastic model introduces elements of randomness so that the answer is different every time. All right, 5. A conditional operator is which type of operation? The correct answer there was a local operation. It only considers one location at a time. Is this location greater than 5 or less than 5? That's a conditional operator, and it's a local operation. 6. Slope is a special case of which type of operation? The correct answer there is focal. Okay, it considers the nearby cells. Okay, depending on the slope operation, may or may not be the same nearby cells, but it's either the 8 or the 4. Those are the 2 versions we talked about in class. All right, simply put, what affect would a neighborhood focal mean or average have on a raster data set? And so the one I'm reading right now said it would generalize the data. That's fine. I was looking for something like it would smooth the data, something similar to that. Number 9 is the correct answer is zonal there. I'm looking for the total amount of people living, where each cell represents the total amount of people living. So what type of operation we use to find the total amount of people living in we left out in, but in various city limits. That would be a zonal. Okay. The cities would be zones. So I'd be saying, okay, how many people live in Hattiesburg? Well, I take the raster data set and use a zonal operation, and the inputs would be the raster data set and the either polygon data set or the raster zone data, and I would get an answer how many people were living inside of the city of Hattiesburg. Okay, fill in the output using weighted linear combination. Use the following factor weights. So what you had to do there was basically multiply everything. Somebody there yet? Hello? Can you hear me on the coast? Can you hear me? Kristen, can you hear me? Okay, good. Great. Right. Okay, we're just going over the test. I'm recording the lecture, so you should be able to get anything that you missed up to this point. I'm on question 10 if you want to follow along. So I'm on the first page. All right, so on question 10 there. Oh, and by the way, the test, the number that on the top is the number you got wrong, and it ended up being out of 70. And so the cutoffs for A, B, C, and D are 7, 14, 21, and 28. Just you know, every 7 points. So 7 and up is an A, 14 and up is a B, 21 and up is a C, 28 and up is a D. That's those are the cutoffs for the grades. Okay, so with factor 1, you multiply factor 1 by its factor weight, which was 1. So really that doesn't change. Then you would take factor 2. Let me see here. Hold on. I can just bring up the test. It might help. See, courses, essay, exams. I guess I didn't prepare on this computer. No, midterm spring too. No, that's not this computer. All right, continue on here. Okay, so so with factor 2 there, question 10, you multiply everything by 0.5. So you get, for all the 3 values, you get 1.5. For the 10 values, you get 5. For 6, you get 3, and so on. And then finally, with factor 3, you'd multiply everything by 2. So you'd get, 4, you'd get the 8, and 9, you would get 18, and so on. And then you add those 3 together using weighted linear combination. That's the correct formula. So you add all those up after you multiply. And the absolute correct answer would be to have 13. Let's see, yeah, 13.5, 22.5, 28. Some people then took the average, and I actually wrote, yeah, you didn't need to take the average there of those values. Okay, that's how you did that one. If anybody has any questions on these as I go through them, stop me. Number 11, this was each factor here had a conditional statement, and you had to evaluate the conditional statement, and then use pass-fail screening to get the right answer. And so, according to what we talked about in class, the pass-fail screening meant that every factor had to evaluate to true, have a value of 1. And so, you guess the writer. Every value had to have a value of 1 for it to be correct. And so for factor 1, if the value was greater than 4, then it got a value 1. So 5, 9, 8, 8, 10, 5, 6 all got 1s, and 3 and 4 got 0s. Okay. And for factor 2, it had to be less than 8. So 5, 6, 7, 4, and 6 all got values of 1, where 10, 8, and 8 got values of 0. Okay. And then we carried that on, and it turned out that basically only the first column and the top one in the second column had 1s in all 3 factors: factor 1, factor 2, factor 3. And so if your pattern looked like that, then you didn't get any wrong, and if it didn't, then you got 1 wrong. If you were pretty close, you just calculated something wrong, and you got 2 wrong if you just didn't understand the concept or didn't demonstrate that you understood the concept. All right, number 12. Number 12 was a little more people got the first 2 right than this one. Lots of people missed number 12, but not everybody. About half of the people missed number 12. So what you did there in number 12 was that the value raster was the first set of the first raster there, the first little small 3x3 raster. The zone data was the second one, and those represent the polygon data. So we have three zones: the 1 zone, the 2 zone, and the 3 zone. And what you should put in the output data was everywhere in the 1 zone, you should put the sum of all of the data that is in the 1 zone. So it should be 7 plus 7 plus 10. That's the sum of all the data that's in the number 1 zone. Like this. So I've got a little thing here, and my numbers: 7, 7, 7, 7, 9, 10, 8, 8, 8, and 5. So the number 1 zone was just this data right here. That's the number 1 zone. So in the output grid, for those 3 cells, you should have 24, right? 24, 24. And just those 3 cells. The number 2 zone was these guys. So that's, I don't have a key in front of me, I left it. What's 8 plus 8 plus 8 plus 7? Whatever that is. That's the number that you should have. So it's really 8 times 4, which is 32 minus 1, so it's 31. 31, and then zone 3 was just these 2. 9 plus 5 is 14. So that was the right answer. Okay. All right, so that was worth 2. Some people received partial credit. Number 13. Number 13, you're only supposed to fill in the center cell because you're doing a neighborhood operation. And without any other direction specified, typically you take a kernel, you multiply all the values, the corresponding values in the value by the kernel, and then add them up. So 0 times 1 would be 0, 0 times 1 would be 0, 0 times 7 would be 0, 7 times 1 would be 7, 0 times 4 would be 0, 4 times -1 would be -4, and 0 times 4 would be 0, 0 times 0 would be 0, 0 times 5 would be 0. So you get 7 added with all those zeros. You'd also add -4 to 7, and -4 plus 7 is 3. So the correct answer was 3. That should be placed in the center of the cell. Okay. All right, number 14. In cost distance modeling, what should the values in the input cost or friction raster represent? What units are they in? Okay, the cost distance modeling, the cost or friction surfaces represent the cost to travel through the cell, either in the X or the Y direction. It's actually one of the weaknesses is that the cost is the same for traveling in either direction. We talked about that a little bit. So it's the cost for traveling through the center of the cell. Okay. What units are there in? They're in whatever cost units the user is working with. Okay, that's what the units are. Okay, in cost distance modeling again, what are the inputs to the cost distance function? That's the cost distance function that shows us the distance away from some thing. So I wasn't really particular on whether you called that the source of the destination, but you needed to have the inputs be the cost friction raster, which was the last question. So you needed that cost raster, whatever you wanted to call that, cost raster, and then you needed to have the source is what you should have written, but I wasn't particular about what you called that. So you needed those two as the inputs. And then what do the values of the output data set represent? The output data set, the values represent the cost to get back to that input source. That's what the output represents. So that was worth a couple of points, and so lots of people got partial credit. Okay, number 16. What is the difference between an analytical hillshade and a cartographic hillshade? And all I was looking for here is something. I mean, you could have answered something as short as where the light source is placed in the model. Okay. So an analytical hillshade is a hillshade where we're trying to model the true position of the sun. A cartographic hillshade is a hillshade where we're trying to present a pretty picture to the user. Number 17, and they usually aren't the same. Number 17, what do the flow values in a flow direction data set represent? They represent, technically, they represent the direction of the steepest drop out of that cell. Okay? If you said something like slope, I probably either gave you partial credit, or if it seemed like you really know what you're talking about, I might have given you full credit. That's the value. It could be you could say the greatest slope out of that cell, and then you would have gotten full credit. But it's not the same as calculating slope for every cell. It's calculating the individual slope out to every nearby cell, all 8 directions. And that is how flow direction is determined. Is that it's that value. Okay. That was worth a couple of points. Number 18, what do the values in a flow accumulation data set represent? More people got this wrong than the flow direction one. But the values in a flow accumulation data set represent the number of upstream cells flowing into that cell. Then how can you use these values to create a data set that might represent streams? I was looking for something like I could set a threshold for that value and use a conditional statement, something like that, to get a cutoff. Because you basically want, is it a stream or is it not a stream? Well, what determines if it's a stream? If its flow accumulation value is high enough water is flowing into that cell. Okay. All right, 19. What do the values in a slope raster? That was also worth a couple points. 19 was worth 4 points, and I do realize now that I switched my D and C. Okay, I just looked for the answer. I didn't care whether you labeled it D or C, but I appreciate some of you pointing it out that I messed up. All right. So what do the values in a slope represent when calculated in a traditional manner? The values of slope represent the degree of change within that moving window, the degree of elevation change. Well, it doesn't really have to be elevation change. It's the degree of change in the values for that raster. Okay, so that was that one. What implication? Oh, is the number of neighboring cells used? No, it's not always the same. And I didn't ask you to describe any further, so if you wrote that, that's fine. What implications does the cell size have on the calculation of slope? Here, the very best answer was that as the cell size increases, the slopes will decrease without changing anything else. Okay, you could say that the slope value wasn't as precise. Saying that it wasn't as accurate was almost on the edge of being a partial credit type of response. It's not really accuracy because technically the slope between those two cells is that. If the values in the cells are accurate, then the slope between those cells are accurate. It's just that we're not being very precise. We're not specifying the value of the slope all the way in between those two values. All right. Okay, your slope, let's see, we're on number, yes, we were on, I just did D, even though I labeled it as D. And then the next one is, if I calculated the average slope for an area, how or why would it be different than calculating the average output value using the Hodgson-Gale method? What I was looking for here was that calculating the average slope doesn't account for the direction of the slope. So if I'm concerned with the average of the slope values for that area, and I just want to know the average steepness of the slopes, I should do the traditional value. If I'm looking for the average directionality of that slope, then I should use the Hodgson and Gale method. So if you have to say something about the direction, the Hodgson and Gale accounts for the direction of the slope in the average. Okay, and then number 20, well, that was worth 4. Number 20 was worth 6. And what time is it? 8 o'clock. I mean, 10 o'clock. Number 6 was the one where you had to show the steps. It probably would be best to draw this one out. I don't mean like make it last a long time. I mean draw it out. I wish I had a black pen. I don't think the people on the coast can see this as well. Let's see if I can get a black pen really quick. I'm pretty sure I have one in my office. It's right across the hall. Got it. All right. Put this right like that so it'll be on the recording. Lower this. Glare won't be as bad. Okay, so we're going to do this last one where we're going to diagram the processes involved in doing the water modeling as we discussed in class. Okay, so we have our DEM. Let's do it. Let's not quite do it. So I got a bad pen. DEM, and I'll just say our pour point. These are our 2 input data sets. Okay, we're not going to use the pour point for a little while until we get to the point where we calculate the watershed. We don't need the pour point until we calculate the watershed. Okay, just the DEM and the pour point data. So we'll start with the DEM. With the DEM, we have to calculate these statistics, or these things like flow accumulation, flow direction, fill sinks. Okay. What's the first one we calculate? Well, if we want to do fill sinks, we do that first. So the input is our fill sinks. I mean, our first our first thing that we could do is fill sinks. If we want to do that, you do it first. So you fill the sinks, and we have our filled DEM. Okay, so if we were putting this in Model Builder, we'd have our filled DEM there. Okay, the next thing is flow accumulation first or is flow direction first? Which one gets calculated first from a DEM? Flow direction, that's right, because flow accumulation needs flow direction. Okay, so the next one, sorry, I'm going to keep this consistent. I don't know if this is, forgot whether ArcGIS uses the circles or the squares, but I'm going to use circles for operations, squares for data. Okay, so I'm going to say flow direction is the next thing, and this is the name of the operation. Just so happens I'm going to call the grid the same thing. I'll just write FD for short. So that's the flow direction grid. I'm getting off the side here, so I'm going to start going up. And the next thing is I'm going to calculate flow accumulation. Yep. And the output's going to be called, I'm going to call it the flow accumulation raster. So this is my flow accumulation raster, the output data set, where every cell in this raster represents the amount of cells flowing into it. Okay. All right. Now I need to calculate the watershed. I need to calculate that. That's a operation to calculate a watershed. What are the inputs? Well, one of the inputs is the pour point. Now, what's the other input? Is it flow accumulation or is it flow direction? It's actually flow direction. Okay, but I didn't always. Well, some people put both of these in and I didn't take off. But flow direction is the input there. So flow accumulation is only really necessary for actually calculating the streams, the stream data. Okay, if I'm interested in finding out where the streams are, I need this. This would be like an input to finding streams up here. But we weren't concerned about that. We didn't ask you to do that. We just said, show the steps involved in creating a watershed. Okay, so this was optional. All right, so we got a watershed. And then the last thing that I wanted you to do, so that was worth 5 there. So we got, you get this operation, you get this operation right, you get this operation right, and you get all the inputs right, then you got full credit. Okay, you got partial credit if you didn't. So that was worth 5 total. And then for the last part, the B part, you had to say, if I also had another raster data set, this is my other raster data set right here. This represents the runoff. And I want to find out how much total water ran off this watershed. Okay, how much total water ran off that watershed. Then all I needed to do was use and you didn't have, I actually gave people credit where they didn't necessarily write zonal sum, but you had to say something like sum, or it was best if you wrote zonal sum, okay? And then your inputs were the runoff data set would be that would be the value raster, and this watershed, actually there should be an output to the, so there should be a watershed. That was the other input was the watershed itself. So the watershed and the runoff, and then you'd have the total runoff in that watershed. That would be the result. Okay, so that was the 6th point, and that would be a totally correct answer. Question?
I don't know for the coast people, it's mirror image on the screen.
I noticed that halfway through it.
Okay.
I can go back over it for the coast people, or take it. Maybe I'll take. Well, it doesn't look very pretty. Or maybe I'll make it look more pretty and then put that up as the correct answer for number 20. That's correct. So it looks, it's mirror image and there's a lot of glare on it. But those are the processes. We've got our DEM. We use that. We fill the sinks. We get our filled DEM. Our filled DEM We calculate flow direction on that, and we get a flow direction data set. We don't have to calculate flow accumulation for this particular problem, but this is where we would if we did. We take our flow direction data set and our pour point data set, and we can derive a watershed for that pour point, because a pour point and the flow direction determine where a watershed is. And then if we want to summarize anything for that watershed, we use an operation like zonal sum, and we feed it the runoff data set. I didn't show them like the modeling of runoff like we did in class. We did that as a separate problem in the lab, and then the output was the total runoff. All right. Okay. Does anybody have any questions about the tests? If you have individual like questions that you want to say, you want to make sure you say, I think that I said what you were saying. Maybe I just need to reread it. That type of thing. You can come talk to me individually if you don't want to do it right now. Then we can do that. Okay, so let's do the lab. I'm recording the lab here as well. Okay. Is it? How warm is it outside? It's kind of getting hot, but. Okay. Oh, that's the slides. Okay. Content labs. Actually, I think I have it open. No, I don't have it open. Lab 6. Okay, so go ahead to the internet and download the lab, and you'll get something that looks like this. Okay. And actually, if you go to the internet and download the reading for the lecture, you'll get this article, and you might want to use it for the lab. Let's see where it is. Table 5.5. Oops. This is I wrote table 5.5. I think I messed up here. Yep. Okay. So this should be table, I'll fix this. This should be table 6.1. This table here, I have no idea why I wrote 5.5. That's a pretty big mistake because it's nothing like table 6.1. So this table right here, we're going to be producing a similar table to this table. Okay, this table here. Here, I'll do it right here so the people on the coast can see. This table right here has method in this column here. So we're going to be testing a few different methods and looking at how they're different, how they're different in their minimum and their maximum. And I'm gonna let you choose this thing right here, this percent area greater than 500, because I'm gonna let you choose you can choose any of the pollution statistics that you want in the data. And you can, based on which one you choose, try to look about halfway in between, okay? So the first one that you do the interpolation, and then look at the minimum and the maximum values, and maybe make this halfway through it. So if your minimum values turn out to be 20 and 180, you could choose a value like 100, 110 or something, and say the percent area over 110, but make it the same for every single one. So what you're going to do is produce these statistics for each one. So you're going to get minimum, maximum, percent area less than X, you choose X, but make it interesting. And then we're also going to compare everything to IDW. So what I'm going to do first is do one in IDW. Okay, so that's what you have to hand in. And again, your IDW example, you get to choose, but you get to choose what you do, but for the one you're going to compare everything to, I want you just to choose the defaults. Okay, so you can compare everything to the default IDW, and then you're going to choose one additional IDW where you get to change something. One of the spline operations, you get to choose the values you do, but I want you to specify what you chose, and then 2 different Krieging operations. Okay, so you're going to have 5 lines in your table. 1, 2, 3, 4, 5. 3, 4, 5. Yep. So you're gonna have 5 lines in your table. You're gonna say, you know, IDW with this input parameters, spline, your Krieging number 1, Krieging number 2, and then you're gonna have the one other that you pick. Okay. All right. So I'll show you what I'm talking about here. It's getting warm. Okay, so I've got it ArcGIS open, but from 2 nights ago. I never turn off my computer. I probably should. Just close the lid. GIS is fun. Okay, so let's add this data in. This is the same data that the book author used in the data set. Actually, I'm going to download a fresh copy so that I don't mess up the copy that I used to upload the lab. So you can do that too. Spatial downloads pretty quick. I'm going to copy this into C temp, paste it. Bam. C temp. Lab 6. All right. Go ahead and actually with this one, I did make a I just remembered I made an MXD that you could open. That will go away eventually. Just an error message. Okay. Go ahead and close down the one where I'm not doing anything. Okay, so this is what you get if you just open the MXD. You don't have to use the MXD. It's really simple. I just added this flood mask, and I added the landmass number 1 and landmass number 2. So I got 2 different land masks. You don't really need this land mask. I just created this land mask so that you do need this one right here, the one that shows up kind of a greenish tan. We only are concerned with the minimum and maximum values within the area that was interpolated. So within this area. So every time you do your interpolation, you need to clip it with this land mask. Okay. Basically multiply, because if we look at what this data set is, we can see that it's all 1s. So just multiply this to your output data set and you'll get it clipped. I'll walk you through that right now. Let's do that. So let's add this soil pollution data set. Okay. That's this data set right here. We open it up and you can use any of these inputs. Okay. Zinc, lead, mercury, cadmium. You can use any of those as the input to your model. Okay. So notice that this isn't a GIS data set yet. Okay, we've got a value here that says northing, and a value here that says easting. There are a few different ways in ArcGIS to turn this into GIS data. Anybody remember from a previous course? There's a toolbox way, but since we're only going to do this once, we don't really need to do it in the toolbox. Probably the easiest way is to just go. I think it's under. Let's see. Where is it now? There it is. They did move it. File, add data, add XY data. Add XY data will get us to do it. So if we choose the easting and the northing to be our XY data, which one's going to be the X and which one's going to be Y? Do you think? Got any ideas? Would easting be X or would easting be Y? East and west run which direction if we're looking at most maps? Yep, east and west. So it runs in the X direction. And that is a little bit tricky sometimes. You got to think about that because latitude and longitude, which we usually say latitude and longitude, right? Now, latitude, does that run east and west or north and south? Right. So latitude and longitude, the way we typically, when we say latitude and longitude, we usually don't say longitude and latitude, although we could, but we don't. And so we're actually saying the X dimension in the reverse order for lat long. But anyway, that doesn't have anything to do with what we're doing now. We've got easting and we've got northing as our X and Y. And if we just hit OK right now, because I didn't really assign this any real projection data. What happened here? I don't know why that. I don't know if yours did the same thing. Just right click on it and say zoom to layer. All right. Now you notice that there's 2 points that are outside the study area. That's fine. Those points can be utilized in the interpolation. They all have values. If we click on these guys, change this to visible layers. Maybe I can get it. Oh well. I'm not clicking precisely enough. One thing that I like to do is that this soil pollution data in its current state is not really GIS data yet. It is in the computer's memory. That's what it means by soil pollution events. It's an event theme. You created it by doing this, but it just drew these dots. It's not pulling this data from data on disk. And so if you wanted to work on it later, you'd have to make sure that you did it in the exact same map document, which you can do. Like if I just hit save right now, I just hit save and I close this down and I open this back up, it should look identical or near identical. If you're on a different machine, it wouldn't look exactly the same because maybe the windows would be in different places, but the map itself would look the same. See that? Okay, but these still aren't stored on disk anywhere. It's just a virtual theme. And if you want to make that permanent, you can data export data, right click, data export data, and save it into the directory you're working in, which isn't this one. See, temp, whoops, temp, and then lab 6, and I'm going to call this, I'm just going to call this soil P for soil pollution. It's going to save it. I got to write soil pollution, change this to shapefile. There we go. And so now it's going to be saved as a shapefile on disk. I can add it to the layer if I want. Then I can get rid of the event layer. And now it's an actual layer on disk. I'll hit save again. All right. So do the interpolations. The interpolators are down here under Spatial Analyst Tools. If you choose interpolation, then you'll get to do these things. So what I mean when I say I want you to do one more IDW, because we're going to do one IDW together, and it'll just be the default. I want you to do another one. You're going to do 2 kriging, 1 spline, and 1 additional one, I think is what I said. You can go back and look at the example here. Okay, so IDW. Let's do that one. Double click on IDW. And we're going to choose our point features are going to be soil P. Now this is where I'm going to let you choose the value field yourself. Observation is not one that's even valid, okay? You have to do one of the pollution ones: cadmium, mercury, lead, zinc. You have to choose one of these. Okay. I think I might have even said you can't do the one that the book did. Right? Let's look at this. Anything but zinc. Okay. All right. So I'll just choose cadmium here. It's the first one. And for the first one, I just want you to choose these defaults. But let's talk about what these do. So this is the output. You might want to actually change that. That's not really what I mean by a default. So we could go in here and say C temp lab 2 or lab 6, and then say output. And inside here, we could put our data set, and we could call this IDW, and we could even name it something. This is going to be, the inputs are the power of 2, and the number of points is 12. So I'll just call it that. IDW2_12. The cell size, it doesn't matter to me what you have it, but it needs to be consistent. It needs to be the same in every single one. Always have the same cell size. So in order to make this easier as a real number, I'm going to change this to 8. Change my cell size to an even number. 8 is good. Okay. And now for every single additional one, you can just change that cell size to 8. And you should get a raster that's exactly on top of the other raster. All right. Okay, so these are the other inputs. We've got the power. Remember, we talked about the power in class last week. That was the R number. Okay. As that number gets bigger, we're going to weight closer points more and more than we are points further away. Okay. And then the second one is really 2 options. You can choose whether or not you want to make your search variable. What that means is I want to pick the number of points I'm going to use. Or if you choose fixed, you're saying I want to choose the distance. Okay? I want to choose the distance. So if let's leave the default there, variable. So for the other one, maybe you could change it. Say I want to choose the distance and pick either a fairly small or a fairly large distance. All right, we're not going to do this at all. Input a barrier polygon feature. A barrier polygon feature will prevent interpolation across that it says polyline, sorry. Will prevent interpolation across that polyline. So in other words, if I had a line running like right through here, what that would be saying is even if there was a raster cell right here where the radius that it chose was like this big, and it got this cell, it wouldn't consider it because it was beyond the barrier. Sometimes this is useful, like in doing interpolation, like in a bay or something, where you don't want interpolation to occur across the land because it wouldn't make any sense. Okay. All right, so now we're going to hit OK. And there's my output. Okay. All right. Now, notice by default, only interpolation is occurring, and that's okay. Okay. If we really wanted to, we could extrapolate into these areas. Okay. We could just under geoprocessing, if we went back and ran this again, we could go under environments and choose for the raster analysis to be the extent, sorry, under extent, the processing extent, and we could force it to be the same as the this mask. Where's the mask? And in fact, we could actually enter that mask in here so that we don't have to do the step I was about to show you. And we could I wonder what that cell size is. Okay, so I made the cell size 10. So just as an example, I'm going to hit OK here. I'm going to run it one more time, and we'll see how it looks different. See how it selected just that area. Okay. And that's not quite what I was imagining that you do. Let me change this real quick. So basically, I have the processing extent here. I was going to say default, so that there wouldn't be any extrapolation. I don't know why it's not redrawing in those. Yeah, there it goes. All right. So that's without any extrapolation, but it's clipping into that area. You could, as an alternative to that, actually do a multiplication. Okay. But I just thought about this as I was doing it. I thought it would be faster to just do just set the environments. So just in case you didn't see that, you can go and set the environment here and change this value under raster analysis. You can change the mass to landmass 2, and then you will not have to multiply the output. If you don't do that, in other words, if your output takes up all this area here, like it's a square, okay, then you have to do the multiplication step afterward. Okay, but that's a slicker way to do it. Okay, when I did the lab, I didn't do that, but I think you should do the slicker way personally, the faster way. Okay, so that's the IDW. All right, so let's do the second IDW. So we can just go up here and rerun the same one that we just ran, because we want to make sure that we leave the other parameters the same. We want cadmium still. And this time I'm going to change this to fixed. I'm going to choose something fairly small, like 30 meters. Well, I don't know if I'm going to get any if I do that. Look at the distance between. Cancel out of this. It won't let me choose distance because I didn't specify what the units were. Well, here, I'll count them, because I made the cell size 10, and so that's a lot of cells. So never mind. Let's not use 10. So if I choose I'm still going to choose fixed width, but maybe I'll leave the default. That says 40. That still seems big. Let's choose an unusually large number instead. So I'll choose like 1,000. Okay. 1,000 is my number. So now I'm going to change this to, and I'm also going to change the power to something different. I'll change the power to 4, and so I'll say 4_1000. That's just the file name to help me remember. Okay. All right, and if I run this from the results, the environments variable should already be set to allow me to choose the land mask. Should already be there. So I say OK. I say OK one more time, and it runs. And now I have both of these data sets. I'm going to close this. Close this for now. Make this big. So now I have this, the IDW 41000 and the IDW 212. See the differences? Okay. How do I get the minimum and the maximum values? I can look under properties, source, and I can look at the min and the maximum values right there. Okay. So it's basically 0 and 18 are my minimum and my max for this particular data set. So it's a really, really small number. And then 18. Now if I look at this one, I get a value of 0 and 18.87. So they're almost the same. Alternatively, if I didn't want to have to go look up these manually, if I actually wanted to produce a report, to produce a table that already had it in there, is there any idea of what way I could do that? In fact, if I did it the way I'm thinking, I wouldn't even really have to do the clip, because what if I did, maybe I'll say it a different way. What if I did zonal statistics on this IDW output, but I did the zonal statistics using this as the zone, this data set right here, this landmass as the zone? What would happen? What would the output be? The output would be a table, and it would have the zonal sum, the zonal min, the zonal max, the zonal standard deviation, and so on. Okay, so you could run that 4 times and produce a result and build your table that way. Okay. All right. One other thing that might be difficult to understand here is I want you to calculate the mean absolute difference from the IDW. So in other words, from this IDW control data set, what's the mean absolute difference? Well, I can calculate that pretty easily by using raster map algebra. So I say I want the difference between this data set and the control, but I want the abs. I think it's, yeah, it's right there. Abs. I'm going to get the absolute value of the difference between those data sets. And I'm just going to call this like AB, ABS, diff. I'll call it A diff because it's going to get too long eventually. Too long. There we go. I called it 1K. Now, alternatively, if you save it in a different format, if I put .img on the end, you notice I did that in a few labs. A .img format doesn't care if it's more than 13 characters, but if you don't put .img, it saves as an arcinfo grid, and it does care if there's more than 13 characters. Okay, so I'm going to say okay here. It's going to run. And this is interesting because this shows the absolute difference between the 2 data sets. Okay? And if I look at this data set, I can see where the differences in my parameters caused the most differences in the actual data set. And so you can see, it caused a lot of difference here. Okay, it caused a lot of difference here. Basically, in areas where there weren't many nearby points, it weighted those nearby points more, and so we saw larger differences. Okay. All right, so you're gonna do one of these for each, but you need to find the average of this. And again, that's the zonal sum. A zonal mean, or I believe that mean is also under properties. So you could grab this right here, this mean value. So that's the mean. So your table, we've gotten the min, the max, these min and max. You don't need that min and max. You need the min and max from the data set in question, and then you need the mean from this data set because that's the mean absolute difference. So let's look back at the lab. So let's just start our table here. So here's our table that we're going to make. Insert table, and it's going to have a space for the interpolation method. It's going to have a space for the min, a space for the max, a space for the mean absolute difference, a space for the number of the amount of cells above a certain threshold. Okay. And we're going to do this for, we're going to have a header, and we're going to do this for 1, 2, 3, 4, 5 other data sets. Okay. So we've got our first one, our IDW for 1,000, and our min, sorry, it was 0, high was 18.0. I'll say our high was, min was 0, max was 18.09. I'm going to round that. Technically, it would be 18.01. Even if I was going to round it to 5 decimal places, that'd still be 18.01. Okay, min, max, absolute diff from the control, which was the control IDW, was this value. Take the whole thing. You can just, actually, even if I round that to like 5 decimal places, it'd still be 0.5. All right, and then this would be, you still have to calculate this. This is the percent area greater than X. And you should choose the X before you start making all of them. In our case, let's say that the percent area greater than X is, we'll just use the mean for this data set. What is it? The mean for that data set is we'll say 2.3. Okay, so how would we calculate that? How do we calculate the percent area greater than 2.3 for all of our data sets? Well, I would use a conditional statement. There are a few different ways to do it, but if you do use a conditional statement on this data set, okay, you could just do con statement on this data set, expression value greater than 3, 1, 0, and then call this PA. You will have to keep track of file names, and then say I'm gonna go in here and make sure that my area is calculated beforehand. All right, so those are my areas that are above 2.3 and below 2.3. And if I open the attribute table, I've got a count. And to get the percentage, I just take the total and divide it by which one represents the area less than 2.3. So that would be this number actually. So take the total, divide it by that number, report that here. Okay. So those are the values that you need to fill out. And really what you'll see is that each of the interpolation methods do produce some different results, but hopefully you'll see a little bit of the patterns of where the different results are being created and how they're creating. It'll help you become more familiar with the interpolation methods. Okay. Does anybody have any questions about what you turn in? So you turn in this, then the other thing that you turn in is the answers to these two questions using this scenario. You're going to calculate IDW by hand just for that little circle. And again, this is to get you a little bit more familiar with how it changes based on the input parameters. So you've got the first one where R is equal to 2, the power is equal to 2, and you're using all of using all the points in the circle. The second one, you're using just the points that are the 3 nearest neighbors. Okay. So the 3 nearest neighbors out of these would be this one, and this one. Just a spoiler alert. It's those three. All right. Anybody have any questions? All right. Well, I say we turn the air conditioner on. And then you can work through your stuff. I'm going to get a drink. Oh, by the way, you can keep your test. Take the test back to my office just so nobody says, hey, you left the test just laying around and somebody should have looked at my grade. You can keep them. I got them recorded.
I know what it does. Yeah.
I knew, but I didn't know. I don't know. It's like, you show how to do something, do something else smart. You just tell me anything. Maybe. I decided what I'm going to do right now. I'm going to figure out some way to do my like my GPS and get it all, I guess, bound around some type of bound call. And I don't know what it's going to be yet or how I'm going to do it. And then I'm going to take basically down for each buyer, so I'll have probably 20 or 30 different boundaries. And then I can do like a spatial frequency in areas my stuff within the subset. But it won't be, it'll be more of a qualitative not really quantitative for the reason I've been before. Just you can't say much because of what that might be more that, but that's my goal is I'm going to do that, present the card and look. This that's up to you. There's no way besides doing any way they usually spatial extent for a fiber speed people said it was about 50. So you like I got that and I got this. This is all I'm getting. Pretty cool. It'll need more than the hotspot house. It's pretty everything like that. Especially since I think it doesn't have that sounds like it's doing that for the same kind of it does, but the thing with doing a hotspot analysis, you can't do that out there. It's like I'm trying to make it as this is statistically what it is, and it's not. And I want to be clear about that. I think it's the same thing here for analysis that I've done instead. But I'm going to ask her if she might still be able to run it. I'm not going to be in my pieces. I can talk to her about it. No rate. I'm going to your husband. everybody, even though it's not my it's that. They don't like it. But, yeah, I was like, also, and I already know how to do it. The first one was like, thinking about this, I was like, maybe I can do it like this. And I was like, about like, add things together and make it great color. But now, well, it's exactly after I like laid down my high or something, thought about what I was saying. I was like, we really did that. That sounds like a whole new thesis. That sounds like work. I'm done with that. So, I forgot. I got, this is what I'm playing now. I got 2 days for it. If it's 2 days, I am on track. I think like everything will go. Will be out of here. Yeah. Of course, then
So you feel literally, you just have a goal for hour.
yeah. Okay. It's just that is yeah. So yeah, I told that this morning. I didn't know. But I got all 2 different things. So well, see, I made the mistake of taking what you had been told and thinking as the gospel and never checking it with anyone else.
Yeah, that's what I wrote on it. I was like, oh, that's what we were looking for. I never had to look at my field. But I thought it was
Right, when I got it confirmed by Caleb on very close to Jennifer, no,
yeah.